Good morning, everyone. In the last lecture, we discussed about the concepts of conformal mapping leading to the polar plot. Now, in this lecture, we will see the procedure of drawing the polar plot leading to the Nyquist plot. So, the first point is the basic purpose of Nyquist plot. You can see the points here. To draw the complete frequency response of the open loop transfer function, we know that the given transfer function will be in the open loop form. Comment on the closed loop stability. To find the number of closed loop poles in the right of S-plane, to find the number of closed loop poles in the right half plane of S-plane by seeing the mapped GH plane. Mapped GH plane in the sense shifted 1 plus GH plane. For 1 plus GH plane, we check the encirclements around origin, but when shifting to GH plane, we check the encirclements around -1 plus J0. Range of K values for closed loop stability. Then to find the relative stability, the Nyquist plot is developed by using the mathematical principle of arguments. So you'll see this example here. You have an S-plane where a point is marked -1 plus J. When it is mapped to GH plane, what happens? That is what we are going to see. So S plus 2 by S plus 1 is the expression for GH. So substituting for S -1 plus J, then it will become -1 plus J plus 2 divided by -1 plus J plus 1, J, which is equal to 1 minus J. So there is a corresponding point in W plane when mapped from the S plane, and that point is 1 minus J. Okay. Similar to this, for every point in S plane, we have a mapped point in W plane. Now the principle of arguments says that if P poles and Z zeros are enclosed by the randomly selected closed path in S plane, then the corresponding GH plane B encircled by the B encircled the origin by P minus Z times. That we have already seen in the previous lecture. So this is a randomly chosen contour. Similar to this, we have another contour here. But P minus Z is here. P is the 1 and Z is 1. Number of poles is 1 and number of zeros is 1. So P minus Z is 0. So there is no encirclement around the origin in the W plane. Now note these points. If P is enclosed in the Nyquist contour of S plane, then there is change in direction while mapping. If Z is enclosed, no change in direction. We've already seen if minus 2 pi is the encirclement in the S plane. That means if clockwise encirclement is there in the S plane, and which corresponds to a pole in the contour, then as pole is in the denominator, we'll have opposite encirclement in the W plane. If 0 is in the contour, then it will be in the same direction. The mapped encirclement will be in the same direction in the W plane. Now conventional sign convention for the direction is for anti-clockwise we take it as positive, and for clockwise we take it as negative. Now number of encirclements about the circle point -1 plus J0 must be equal to poles of characteristic equation, which are open loop transfer function poles in the right of S plane. You can see here n equals P plus minus Z plus. Z plus is the closed loop poles in RHP. This is what we are interested in, because we need to check the closed loop stability. For that, we need to check the number of closed loop poles in RHP. P plus is the open loop poles in RHP. Our given function is open loop transfer function. So from there we can get this. And after mapping to the W plane, we will get the number of encirclements also. So basically we will know N and P plus. From there we can find Z plus, and from there we can comment on stability. Now procedure to draw polar plot. Find the magnitude and phase at omega equals 0. That means when the transfer function is given, you have the expression for magnitude and phase. There we will substitute omega equals 0 So magnitude at omega equals 0 we'll evaluate, and phase at omega equals 0 we will evaluate. Similarly, we will evaluate magnitude at omega equals infinity and phase at omega equals infinity. Now we need to find the ending direction and starting direction. To find the ending direction of the plot is given by phi 0 minus phi infinity. Phi 0 is the phase angle evaluated at omega equals 0. Phi infinity is the phase angle evaluated at omega equals infinity. So we take phi 0 minus phi infinity and we evaluate that. If this is positive, then the ending direction is clockwise. If this is negative, then the ending direction is anti-clockwise. Okay, you will understand this better when we move on to examples. Starting direction is considered on the basis of negative real poles and zeros. If finite poles are near to the imaginary axis, then starting direction is clockwise. That means if both poles and zeros are there, and if pole is nearer to imaginary axis, then we say that the starting direction is clockwise. If zero is nearer to the imaginary axis, then starting direction is anti-clockwise. Now the above procedure is valid only if magnitude at omega equals 0 greater than or equal to magnitude at omega equals infinity. That means the polar plot is valid only if magnitude evaluated at omega equals 0 is greater than or equal to magnitude evaluated at omega equals greater than or equal to magnitude evaluated at omega equals infinity. Now let's see an example. G of s into h of s equals 1 by s plus 1. The first step is to replace s by j omega. We substitute s equals j omega here. So it will become 1 by j omega plus 1. Now we find the expressions for magnitude and phase. So magnitude of gh becomes 1 by root of omega squared plus 1. And angle of gh becomes 0 minus tan inverse omega, which is minus tan inverse omega. Now the next step is to find m0 m infinity and phi 0 phi infinity. That means at omega equal to 0 and omega equal to infinity, we are going to evaluate both magnitude and phase. So m0, what is m0 here? M0 is 1 by root of 0 plus 1, which is 1, and m infinity is 0, right? Phi 0 is 0, right? Phi 0 is here. Phi 0 is 0, then phi infinity is minus pi by 2. Now we'll see whether the polar plot is valid or not. The basic condition, we'll check m0 greater than m infinity, right? This is a condition, m0 greater than or equal to m infinity. So this is satisfied here. M0 is greater than m infinity. So the polar plot is valid. Now we move on to the procedure, the detailed procedure. So what about the ending direction? How will you find the ending direction? You will evaluate phi 0 minus phi infinity, right? 0 minus pi by 2, which is pi by 2, plus pi by 2, which is positive. So clockwise direction. Ending direction is clockwise. Now what about the starting direction? Only one finite pole here. There are no zeros, one finite pole here, and that pole is near to the imaginary axis. That is what is our assumption, because there are no zeros, so relative distance from the imaginary axis cannot be found, right? So the direction is, starting direction is clockwise. Now we will draw the plot. For omega equals 0, you get m equals 1, then omega equals infinity, m equals 0. Then corresponding phase at omega equals 0 is 0 degree, and phase at omega equals infinity is minus 90 degree. Now you see how we'll plot the polar plot. So you see the axis here. This is 0 degree. This is 90 degree. This is 180 degree. This is 270 degree. Or this is 0 degree. This is minus 90 degree. This is minus 180 degree. This is minus 270 degree. Now we have to find the starting point from for that we have to see from which axis, which part of the axis we'll start this. So you see here for omega equal to 0, phi 0 is 0, right? Phi 0 is 0, so it will start from this side, 0 degree side. Now from which point it will start in the 0 degree axis? To find that, we have to evaluate m0. M0 is 1, right? Magnitude is 1. So at point 1 it will start. Okay. Now we need to get the starting direction. The starting direction is clockwise, right? So it will move like this, clockwise. Now what is the ending is here? Ending direction is also clockwise, right? Clockwise in the sense, now what will happen is we need to find phi infinity also. Phi infinity is minus 90 degree. So the endpoint of the plot will be asymptotic to the minus 90 degree axis, and it should be clockwise. And the endpoint should be, the point should be, the termination should be at m infinity. M infinity is 0, right? M infinity is 0 here. M infinity is 0. Okay, so it will terminate at 0 point, asymptotic to the minus 90 degree, right? Asymptotic to the minus 90 degree axis, and the ending direction is clockwise. Starting direction is clockwise. It will start from 1. Okay, so this is the polar plot. Now, as an extension, what we are going to do is we are making some changes in the function of GH. Now it has become 1 by s plus 1 into s plus 2. So now you see that there is a change in polar plot. It has become like this. That means it has entered into the next quadrant, right? It has entered into the next quadrant. So earlier it was 1 by s plus 1. Now it is 1 by s plus 2. 1 by s plus 1 into 1 by s plus 2. Now we have again changed it to 1 by s plus 1 into s plus 3. So now you can see that it has entered into the next quadrant compared to the previous expression 1 by s plus 1 into 1 by s plus 2. When one more pole is added, you see that it has entered into the next quadrant. So addition of each finite pole shifts the ending angle by minus 90 degree. Earlier it was minus, in the first problem it was minus 90 degree, right? In the second problem, what was it? It is minus 180 degree. The ending part of the plot is asymptotic to the minus 180 degree axis. Now, when one more pole is added, s equals minus 3 is added, then what happened? It is now asymptotic to the minus 270 degree axis. That means again minus 90 degree shift has happened. So this is a generic guideline. Addition of each finite pole shifts the ending angle by minus 90 degree in the clockwise direction. Everything is in the clockwise direction. The end point is always, the ending direction is clockwise. Now, for 1 by s plus 1 into s plus 2, we know the generic pattern of polar plot from which we can find the point of intersection. That means here you need to find the point of intersection also. You know that this is this part of the axis corresponds to phi equals minus 90 degree, and you see that there is a point of intersection for 1 by s plus 1 into s plus 2. So you need to find this particular point. How to find this? You can see two different points are there. One is one intersection is on the phi equals minus 90 degree axis, and another intersection is on the phi equals minus 180 degree axis. So both we have to find. Now to find the point of intersection, phi equals minus 90 degree, you apply phi equals minus 90 degree in the expression for angle. Angle of GH we know, right? Angle of GH is minus tan inverse omega minus tan inverse omega by 2. For this one, 1 by s plus 1 into s plus 2, the angle is minus tan inverse omega minus tan inverse omega by 2. When omega equals at phi equals minus 90 degree, we get omega as root 2 radians per second. Root 2 radians per second, because for angle GH we substitute minus 90 degree, then we evaluate omega. Omega you get root 2 radians per second. So now with this omega you evaluate the magnitude. When you evaluate the magnitude for this particular omega, you will get the intersection point here, this intersection point at the minus 90 degree point. Similar to this, in the next problem you have an intersection point on the minus 180 degree axis. So phi equal to minus 180 degree, you apply phi equals minus 180 degree for angle of GH, find omega from there, apply that omega on the magnitude, right? Then you will get the intersection point here, the intersection point you will get. Now, okay, so solve these two problems as homework. I mean, the point of intersection you find it as homework. Now we'll move on to the next problem. GH equals 1 by s into s plus 1. Again, s equals j omega is substituted. 1 by j omega into j omega plus 1. Similar procedure we follow. The magnitude expression is found out, 1 by omega into root of omega squared plus 1. This is evaluated at omega equals 0. So we get m0, which is infinity. Then we substitute omega equals infinity here. We get so m infinity equals 0. Now we check the condition for valid polar plots. M0 greater than or equal to m infinity, polar plot is valid. Now we move on to the detailed procedure. So we find the expression for angle minus 90 degree minus tan inverse omega, right? Minus 90 degree minus tan inverse omega. Now we substitute omega equals 0. So phi 0 is minus 90 degree, tan inverse 0 is 0. So minus 90 degree, phi 0. Then phi infinity is minus 180 degree, minus 180 degree. Now to find the ending direction, we evaluate phi 0 minus phi infinity. That means minus 90 degree minus 180 degree, which is plus 90 degree, which is positive. So clockwise direction. Ending direction is clockwise. Now starting direction is always by finite poles or zeros, but here we have pole at origin. Hence, we cannot find the starting direction from the prescribed guideline, right? But what we need to do here is we have only s equals minus 1 is the finite pole. We don't have zeros. So whatever is near to origin is pole only. So we take it as clockwise direction, clockwise direction. Okay. Now we are going to draw this. To draw this, what should be done? You need to find the starting direction first. What is the starting direction? Starting direction is clockwise, right? Starting direction is clockwise. And what is the starting magnitude? That is m0. What is m0 here? M0 is infinity. So now we need to get the starting angle also. To get starting angle phi 0, you need to find phi 0 is minus 90 degrees. So it should start from this part of the axis, minus 90 degree. And it should come from infinity because m infinity, m0 is infinity. Okay, so it should come from infinity. It is coming from infinity. Now the starting angle is clockwise, so it should go like this. It is clockwise, right? Now what about the ending direction? Ending direction is also clockwise. Okay, now what about the m infinity? M infinity is 0, right? So it should terminate at origin. M infinity is 0 and it should be clockwise. So this is clockwise. Now we need to get the ending angle. Ending angle is 180 degree, minus 180 degree. Here, this is the axis for minus 180 degree. So the ending part of the plot should be asymptotic to the minus 180 axis. Ending direction is clockwise. Termination point is 0. Starting point is infinity and starting angle is minus 90 degree. Starting direction is clockwise. So this is what we get. Okay. Now we'll move on to the Nyquist plot later. This is just the polar plot. And we know that polar plot is plotted for 0 plus 2 plus infinity. We have not, till now we have not considered 0 minus 2 minus infinity part. That is, we have to plot the mirror image of this one and we have to combine both. So, it will be symmetric. So, how would be the Nyquist plot looking like? It will be like this, you see. It is the first part is this and the second part will be like this. Okay, like this. But I'll draw this later. I'm just telling you the qualitative analysis, how it can be done. The mirror image you take like this and both you will consider for Nyquist plot. Okay, and symmetric, right? These two are symmetric. Now note the pattern here. What is the pattern here? GH equals 1 by s plus 1, right? GH equals 1, addition of finite pole shifted ending direction by 90 degree, right? 1 by s plus 1. This is the polar plot. Now addition of pole at origin. What is addition of pole at origin? Here addition of pole at origin in the sense 1 by s into s plus 1. Earlier it was 1 by s plus 1. Now it is 1 by s into s plus 1. So addition of pole at origin shifted the entire plot by minus 90 degree, right? This was the plot earlier, right? Now the entire plot is shifted by minus 90 degree, right? Here the starting point itself is shifted. It was starting from here. This is the 0 degree axis. Now when it starts from here, what is this? This is minus 90 degree, right? So it starts from here. The entire plot, the ending direction also shifted, right? The entire plot is shifted by minus 90 degree. Now here GH equals 1 by s plus 1 into s plus 2. If this was the transfer function, you got the polar plot like this, right? Now here we are going to add a pole at origin. So it will become 1 by s into s plus 1 into s plus 2 here. This 1 by s into s plus 1 into s plus 2. So similar to the earlier diagram, the entire plot will shift by minus 90 degree. So here also the entire plot is shifted by minus 90 degree, right? Compared to which one? Here only we added a pole at origin. Okay, so because of that, the entire plot is shifted by minus 90 degree. You may not use this actually. This is a shortcut we can go for. Separate evaluation of phi 0, phi infinity, m0, m infinity, starting direction, ending direction, starting magnitude, ending magnitude, and you can draw it. That is possible, but this is just a guideline. Okay. Now we will proceed with zeros. Till now we have seen how the plot will look like if poles are added. Two examples. One is when finite poles are added, and the second one is when pole at origin is added. Now we will see how it will look like when zeros are added. Maybe we can have a break now, and we'll see this in the next lecture. Thank you.